Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. IPv6 transition technologies are designed to support the gradual evolution of global networks from IPv4 to IPv6. In this episode, we will examine the various mechanisms used to ensure compatibility and functionality during this long-term shift. Because IPv6 is not directly compatible with IPv4, organizations require bridging technologies to enable communication between these protocols. Transition technologies allow new IPv6 networks to coexist with legacy IPv4 systems, supporting users and services during migration and minimizing disruptions in environments with mixed infrastructure. The Network Plus certification exam includes specific objectives on IPv6 transition mechanisms. You will likely encounter scenario-based questions that describe a network condition or deployment goal and ask you to identify the appropriate solution. Whether the scenario involves tunneling an IPv6 packet across an IPv4 path or enabling IPv6-only clients to reach legacy IPv4 services, the exam requires you to understand how each transition method operates. Knowing the differences between dual stack, tunneling, and translation will help you select the best approach for each situation. Dual stack is one of the most important and flexible methods for transitioning to IPv6. In a dual stack environment, network devices are configured to run both IPv4 and IPv6 protocols at the same time. This allows devices to communicate with others using either protocol, depending on the address type of the destination. Dual stack offers the smoothest transition path as it enables parallel support for both versions of the Internet Protocol. This allows new IPv6 capabilities to be introduced without disrupting IPv4-based services. Under dual stack operation, a device maintains both an IPv4 stack and an IPv6 stack. When a packet is sent, the device determines whether to use IPv4 or IPv6 based on the destination address. For instance, communication with a dual-stack peer might use IPv6 if available, while connections to IPv4-only devices continue using the older protocol. This model supports a gradual rollout of IPv6 without requiring a sudden infrastructure overhaul. It also ensures that services remain accessible during every stage of deployment. Implementing dual stack requires more than just enabling IPv6 on routers and workstations. The operating system must support both protocol stacks, and applications must be IPv6 aware. Dual stack networks also require routing protocols that can carry both IPv4 and IPv6 routes, as well as DNS servers capable of handling both A and Quad A records. Infrastructure devices, such as firewalls, switches, and proxies, must also be configured to interpret and forward both types of traffic. Without full support across the stack, dual stack operation may fail or perform inconsistently. Tunneling provides an alternative to dual stack when IPv6 cannot be routed directly across an IPv4-only path. Tunneling encapsulates IPv6 packets inside IPv4 headers so they can traverse networks that do not natively support IPv6. This technique was especially useful during the early stages of IPv6 deployment, allowing segments of IPv6 to connect through an IPv4 internet. Tunneling is considered a temporary solution and is typically phased out as native IPv6 connectivity becomes more widely available. One common tunneling method is 6-to-4, which automatically derives IPv6 addresses from IPv4 addresses. This method uses a fixed IPv6 prefix combined with a public IPv4 address to construct a globally unique IPv6 address. While 6-to-4 was widely used during initial experiments with IPv6, it is now deprecated due to reliability issues and operational complexity. It requires relay routers that support 6-to-4 tunneling and was not suitable for use behind network address translation devices, which further limited its utility. Pareto is another IPv6 tunneling protocol, specifically designed to work through network address translation devices, or NATs. Teredo encapsulates IPv6 packets in IPv4 UDP packets, allowing them to be transmitted through home routers and enterprise firewalls. It was primarily used in Windows environments where direct IPv6 support was not yet available. Although it played an important role in the early adoption of IPv6, Teredo has also been largely phased out in favor of native support and dual-stack configurations. ICATAP, or Inter-Site Automatic Tunnel Addressing Protocol, is a technology used to support IPv6 routing within an enterprise network. Unlike Teredo or 6to4, which focus on internet-based communication, ICATAP operates within an internal environment by treating the IPv4 network as a virtual link layer. It enables IPv6 traffic to be routed across an IPv4-based LAN without requiring changes to the physical network infrastructure. ICATAP is useful in environments where administrators want to test or gradually introduce IPv6 without reconfiguring routers and switches. Another transition method involves translating between IPv6 and IPv4. This includes NAT64 and DNS64, which enable IPv6-only clients to reach legacy IPv4-only servers. NAT64 translates IP headers between the two protocols, mapping IPv6 addresses to IPv4 and vice versa. DNS64 complements this by rewriting Quad A queries to return synthesized IPv6 addresses based on existing IPv4 records. Together, these technologies allow seamless communication without requiring the server to support IPv6 natively. It is important to understand the distinction between tunneling and translation when planning a transition. Tunneling preserves the original packet headers and simply encapsulates them in a format that can traverse an incompatible network. Translation, on the other hand, modifies the packet itself, changing address headers and sometimes protocol fields to ensure compatibility. The choice between tunneling and translation depends on whether you want to maintain end-to-end protocol consistency or convert traffic for destination compatibility. Each approach comes with trade-offs related to performance, transparency, and complexity. For more cybersecurity content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Transitioning to IPv6 involves careful planning to ensure that existing IPv4 services remain uninterrupted while new IPv6 capabilities are introduced. One of the first steps in this process is assessing the organization's current reliance on IPv4. This includes identifying which systems, applications, and network devices support IPv6 and which need to be upgraded. Hardware such as routers, switches, and firewalls must be evaluated for dual-stack capabilities, and software components, including operating systems, DHCP servers, and domain name systems, must be verified for compatibility. Without a full audit of current infrastructure, transition efforts are likely to encounter roadblocks or unexpected failures. Selecting the right transition method depends on the specific needs and constraints of the organization. Dual stack is the preferred solution when full support for both IPv4 and IPv6 is available, offering the greatest flexibility and ease of management. However, in cases where IPv6 paths are incomplete or IPv6 adoption is limited, tunneling provides a short-term workaround by encapsulating IPv6 packets for transport across IPv4 infrastructure. Meanwhile, translation methods such as NAT64 are useful in isolated IPv6 environments that must reach IPv4 resources without relying on IPv4 stack support on the client side. Routers and firewalls must be configured carefully to support transition technologies. These devices must understand and handle both IPv4 and IPv6 traffic, including inspecting and filtering based on each protocol's specific characteristics. Dual-stack networks may require parallel rule sets for both protocols, while tunneling introduces encapsulated traffic that may not be visible to traditional inspection engines unless properly decoded. Translation methods also demand careful configuration to ensure that port mapping and address rewriting are done correctly, preserving connectivity and preventing exposure of unintended services. The domain name system plays a vital role in environments using transition technologies. DNS servers must be able to resolve both A records for IPv4 and quad A records for IPv6. Dual-stack clients use these responses to decide which protocol to use when initiating communication. In translation scenarios such as NAT64, DNS64 acts as an intermediary by synthesizing quad A records from existing A records. This allows IPv6-only clients to resolve addresses even when no IPv6 record exists, enabling communication with IPv4 servers through protocol translation. Security remains a significant concern during the transition process. Tunnels can create security gaps by bypassing traditional inspection tools that are unaware of encapsulated IPv6 traffic. If a firewall is not configured to inspect tunnel headers or UDP payloads, malicious traffic could traverse the network undetected. Translation, on the other hand, may inadvertently expose legacy services to public IPv6 networks if address mappings are not strictly controlled. Security policies must be updated to account for both IPv4 and IPv6 traffic, ensuring that access control, logging, and threat detection apply equally across both stacks. Testing and monitoring tools are essential for verifying that transition methods are working correctly. For dual-stack environments, tests can confirm whether both stacks are operational and whether applications are choosing the correct protocol. Tunneling should be validated by tracing encapsulated packet paths and checking for signs of packet loss or misrouting. Translation systems need to be monitored for mapping consistency and translation errors. Logging tools should capture both native and translated sessions, enabling administrators to trace communication across the network regardless of protocol. Despite best efforts, several common pitfalls can arise during transition. One is a misconfigured dual-stack implementation, where either the IPv6 or IPv4 stack is improperly routed, resulting in unreachable services. Another is tunnel failure, which can occur when encapsulation headers are blocked or stripped by intermediate devices. In translation environments, inconsistent DNS responses can prevent clients from accessing resources if synthetic addresses are generated incorrectly. These issues often stem from lack of documentation, insufficient testing, or misunderstanding of how the technologies interact. The Network Plus certification exam includes questions that require you to identify transition technologies based on specific requirements or network constraints. You may be presented with a scenario where legacy services must be reached from an IPv6-only network or where encapsulation is needed to pass through IPv4 infrastructure. Understanding when to use dual stack, tunneling, or translation allows you to answer these questions correctly. You should also be able to match specific technologies like Teredo 6-4 and NAT64 to their characteristics and limitations. To become fluent in transition planning, it is helpful to compare transition technologies side by side. Dual stack maintains two parallel protocol stacks and is ideal when both protocols are fully supported. Tunneling allows for protocol preservation but adds overhead and can create routing challenges. Translation introduces protocol conversion and removes the end-to-end transparency of the original packet, but it enables direct communication between otherwise incompatible systems. Each approach has specific configuration needs, and understanding those requirements will make you more confident in both exam settings and professional environments. In summary, IPv6 transition technologies, including dual-stack tunneling and protocol translation, allow modern networks to support IPv6 adoption while maintaining compatibility with IPv4 systems. These technologies offer flexible paths for migration, whether that involves running both stacks in parallel, encapsulating traffic across legacy infrastructure, or translating protocols at the network edge. Mastery of these options is crucial for ensuring seamless network operation during the transition phase. On the Network Plus exam, demonstrating your understanding of these tools confirms your readiness to work with evolving Internet standards. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.